Welcome back. Okay, today we're going to talk about regularization, a particular type of regularization that helps with problems such as error growth. So previously we talked about truncating our SVD, and that was nice. It enabled us to kind of get a handle on problems that could be introduced if we have small singular values by just eliminating them. The problem is we have to calculate our SVD in order to do that, and that's a lot of work. Is there a better way? So let's talk about regularization in general first. Regularization is when you put some kind of a constraint, usually associated with a prior belief, on your solution. And so we want to minimize as before. We want to choose rather x that minimizes our observation error. So we choose an x that minimizes the difference between our observation and a times x. That's our goal, and we've talked about that. But with regularization we say, but also we have some constraints on our x. And in this case we're going to use delta x like this. In other words, this term right here penalizes the size of x. One way of thinking about it is it's saying we have a prior belief that x should be 0 or close to 0, and inasmuch as x gets away from 0, we're going to increase the cost of our cost function there. So if delta is large, we place great importance on keeping x small. And of course, if delta is small, we really don't care much about the size of x. Instead, we place greatest importance on finding the best solution to our fundamental equation y equals ax. So the question is now how to choose delta. So in many optimization problems, if you've encountered such, people tweak things and they try it out and they see if the solution presents itself and they change it again. We're actually going to give you a little bit more guidance on how to choose this, but there's still a little bit of the trial and error component to it also. So just like we did before when we were looking at our SVD notes, or developing SVD, so as in the SVD notes, we're going to break up x and y in terms of the basis vectors from the SVD decomposition of A. Now, for any x, y minus ax is equal to u b plus u naught b naught. Remember our beta. Our betas and our alphas are vectors. And then we have our SVD decomposition. V alpha plus V naught, alpha naught vectors. We can factor out our u terms, beta minus sigma alpha, because our V transpose V is an identity matrix, so that goes away, simplifying things a bit, plus u naught beta naught, and we also have that V transpose V naught is going to be equal to 0, so that part goes away. So now we have our u naught beta naught comes down, and our u beta comes down, and all that's left of the right hand side is u sigma alpha. Okay, so now that we've got that, we can go a step further and look at the magnitude squared, because this is what we're really concerned with. This is for some arbitrary x, and we get beta minus sigma alpha squared. And once again, using our Parsifal approach, we get this. Mainly, this comes because since u naught transpose u is equal to I, so it disappears in that second term. And we also have cross terms all disappearing because u transpose u naught is equal to 0, and of course u transpose u is equal to the identity matrix. So all these u terms disappear, and what they serve to do is basically ensure that we don't have cross terms involving beta naught and beta. And we also know that x squared is equal to alpha squared, the norm of alpha squared, like that. Okay. So we now have y minus ax plus alpha squared. Remember, this is the term that we're minimizing. From up above, that's just equal to beta minus sigma alpha squared plus beta naught squared plus delta times alpha squared plus delta times alpha naught squared. Okay, well, we're trying to minimize this term, and we have these alphas and alpha naughts and beta naughts. So just as with our standard least squares, we can set our alpha naughts and beta naughts to zeros. So as a result, we're now going to get that expression above is just equal to beta minus sigma alpha squared plus delta alpha squared. Well, what is this? Let's go back to our definition. If we don't know what to do next, we're always safe going back to our definition. I'm going to give myself a little more room. That's equal to the sum over R, capital R. We're no longer using our R prime as we were before, for what it's worth. Beta k minus, that's R, beta R minus sigma R alpha R squared. And then we'll have a, that would be it, but we have a second sum that looks identical, except that it also adds in delta times alpha squared R, so we can just include that in the sum and put it all together. So we're trying to minimize this with respect to x, but since x is determined entirely by alpha, then we're going to take the derivative of that. Now I'm going to not write the whole thing out. Let's actually, let's go on to the next page because we're going to run out of room if we don't. Copy. Paste. There we go. So, to minimize with respect to x, we find the derivative of 1 with respect to alpha sub k or alpha sub r set it equal to 0 and solve. So the derivative with respect to alpha sub r of 1 is just equal to I'm going to change things around just a little bit here for reasons it'll be apparent later on. Okay, so what did I do? I said I'd change things around a little bit. I want to make sure that you realize I'm not doing any hocus pocus. We're taking the derivatives of sums, and we're concerned with the derivative with respect to alpha r. So this sum out front disappears because all the terms, except for the choice of a particular r, will be constants relative to that r. So in other words, there's only one term which will have a non-zero derivative with respect to alpha r for a particular alpha. Then I change the signs around inside this beta r minus alpha r. Oh no, I didn't. Sigma r times alpha r, because when we take the derivative with respect to r, we get this negative alpha r comes out front, and then using the chain rule, we just multiply that by the derivative of the function itself, so we get negative alpha r times 2 beta plus, and here the sign change, 2 times, and now we have alpha r squared, or sigma r squared alpha r. Okay, and we'll set that equal to 0, like so, and we can easily solve for alpha r that minimizes this as sigma r over sigma r squared plus delta times beta r. So we can express this in matrix form in this manner, matrix vector. So we'll have alpha, do TIK, not for TikTok, but for Tikhonov, sigma squared plus delta. So that's a diagonal matrix, so you need to put an I in there. This delta I, inverse. So now every element is 1 over sigma squared plus delta. Multiply that by sigma, and every element on the diagonal is now, as you see described above, sigma r over the quantity alpha, or sigma r squared plus delta. And then that's times our vector B.